Good afternoon again. Back to Apologetics 101. We have spent the first two of our sessions with two main ideas. And in your notes, if you've brought your notes, and I'll only be up for about 6 minutes because primarily what we're going to be doing is watching another video. Now, we've looked for two sessions, hearing me speak a little bit and then watching some videos, because why would you believe me when we're talking about very high-powered scientific ideas? So that's why I use videos. And when I taught this class in the Philippines, as a matter of fact, the idea was for me to make sure they understood what they were about to see, then showed it, then we discussed it. Now, I'm not having to do that with you. We don't have time anyway. So I'll sort of tell you ahead of time a little bit of what it's about. But what you get in these pages of notes that you have is your ability to simply show these same kinds of videos with a basic explanation about the creation of the universe. It was real, it really happened, and this is the scientific community's absolute position at this point. You would be hard-pressed to find anybody who did not believe there was some kind of creation. So we studied that. We watched videos to back that up. What position then does that put a skeptic into? Well, it makes him or her think twice, and he has to concede to some degree that the creation of a universe implies a creator. Why was this significant, did I explain to you? Because 40, 50 years ago, the steady state theory was really prevalent. What is the steady state theory? That's the idea that matter, space, and time and energy are simply eternal. They're eternal, so they don't have to be explained, and therefore you don't have to have a creator. But now we know there was a creation of the universe, therefore they're in a precarious position. And I, as a former skeptic, would have been very much in a more precarious position had I had that information when I was debating this so much of the time as an undergraduate in philosophy and then as a graduate philosophy student at Texas Christian University in Fort Worth. Now, point number one then, when you're discussing apologetics with somebody, go straight to page 11 of your notes, and this is where you want, in my opinion, if you've got a somewhat scholarly type, somebody who thinks they're pretty clever, and I'm not speaking disparagingly, it could be a student, whatever. And I've run into this recently a number of times, and my response to them or the way I speak to them is, oh, you're a skeptic. You know what? I used to be a skeptic too. And do you know what has been discovered by scientists? This is their consensus opinion that there was an actual point-time creation of the universe. Did you know that? And so that destroys what was called the steady state theory. Now, you can go to the videos we've watched that are listed. They're listed here, the things that you've watched. You can be sitting around in a coffee house and talking to them and just punch in the video and let them watch the videos that we've been looking at. So you do not have to become the great expert. I'm not a great expert. I can state to you, though, like a lawyer, like Rick Patton's out here. He's my good lawyer buddy friend. What do we do as attorneys? And this is how we tried to set up originally, talking about preponderance of the evidence. We tried to establish some base work. What does preponderance mean? It simply means about 50%. And in a civil trial, slightly over 50 gives you basically the win. Now, if we were in a criminal trial, what's the term we would use? Beyond any reasonable doubt. But I tried to convince anybody who's a skeptic, doesn't it make more sense to just, you go from no evidence in your mind to if I can show you some substantial evidence, preponderance, or get me close to it is the way I thought about it when I was a skeptic. Just get me close without me believing that Christians are believing something absurd, Just get me there. Well, I went not only there, I got to where I thought this was beyond any reasonable doubt. So number one point then is what? Number one point is there was a creation. If there was a creation, this implies a creator. Does this prove Christianity? Of course not. We're only trying to get them to be open-minded enough to accept a theistic possibility. When you're talking to a skeptic, it's almost certain that you're dealing with either an agnostic who says, I don't know if there's a God, or an atheist who denies the existence of God, usually is much more aggressive about it. Point number 2 that we took up on page 11 once again was what? Fine-tuning. You had videos on that week before last. We skipped a week. And the fine-tuning is remarkable. That one of the leading skeptics in the world, I showed you a video of him fairly brief, and he said, the thing that argues most strongly in his mind for a creator is fine-tuning. The cosmological constant. Remember, we repeated that term. You don't have to memorize it. You just show them your videos. Where do you get copies of that? From page 3, 4, and 5 of your notes. And you have to practice a little bit because you have to know where they are. So there are 15 or 20 or 30 people in here that could really get good at this. And that's what I'm suggesting that you do. Third thing that's up, aside now from the phenomenon of fine-tuning these 24 amazingly precise laws and quantities that just have to be so exact, it definitely implies, in fact, one of the atheists said, he just shook his head and he said, you just can't really deny that something's at work here that we can't really explain. And remember that video of him, and it was atheist physicists prove God. Remember that? All right, that one. That's it. That's the one that you want to go to show somebody once you give them a little background, because these 4 guys that are talking are not believers, but they have been shook. They have been shook. So you want to take that nice skeptic and take them from that position to preponderance of the evidence position. Now, the third thing we're going to look at, it's going to be tonight, is so remarkable. It's more, again, of fine-tuning, the fine-tuning issue. But on top of that, they're going to take us to how we on this earth are so positioned in A, the solar system, B, the Milky Way galaxy, so that we can actually see and understand the entire universe. And it would be so easy. It looks to me like, from what I've seen, more like about 97% odds that we would not be able to know a thing, because we would be buried inside stellar dust clouds, and you wouldn't be able to see out of them. This is the idea of being so positioned, especially moon, sun, to be able to tell us remarkable things. How is this possible that we can know all this? Now, this comes from the book Privileged Planet and another book called Rare Earth. Those books are phenomenal books. We've got the video, and it's publicly available for you to just, pop that thing right on and you're watching it. I want you to write this down too in preparation for the number 5, 6, and 7 lecture that we will have. It's not in your notes. You will simply YouTube a search, YouTube Debate 163, Debate 163, and then type in James White. James White, Debate 163. That's a YouTube search. He's having a debate with a heretic named Ehrman, E-H-R-M-A-N, who is a professor at UNC. Despite the fact I'm for them winning the basketball tournament, nonetheless, he's so off base. This is stuff that I studied in seminary and knew the answer to, but James White does such an articulate job with his graphics. This has to do with what is the Bible. Are there so many mistakes in the Bible from its translations? You've got to see this, and we'll study it in lectures around 6. But really, this will prep you and get you ready for it. So once again, I want you to YouTube Debate 163, James White. James's part of the debate starts at minute 30. So if you don't want to listen to Bart, which is the first 30 minutes, you can just listen to the second 30 minutes of Dr. White. And that 30 minutes is going to give you'll look at it and look at it and look at it. And so I'm asking you, please take a look at that and prep for the next series of studies that we do. Next, please, you should have read through page 20 in your notes. Please finish to page 125. We're about ready to start the video. And we will go for 40 minutes. So get your popcorn out. Don't upset the pastor. Get your popcorn out and really enjoy. I hope you really enjoy this. You're going to see 2 things. A lot more on fine-tuning, but not just fine-tuning. They're going to take you into privileged planted. We are on a special planted that as far as we can tell, in looking in the SETI project, which is supposedly trying to find extraterrestrials, there's nothing like us. And there can't be anything like us for at least 90% of the rest of the universe. Okay, let's start with Privileged Planet.
In liquid form, water is an extraordinary substance, and its existence hinges upon another factor essential to complex life: a planet's distance from its home star.
It's like what they say in real estate: location, location, location. A habitable planet lives in what we call the Goldilocks zone. It's not too hot, it's not too cold, it's just right. And when I say just right, I mean just right for water.
Liquid water really helps define the habitable zone. If it's too hot, again, the water just boils away. You just can't get condensed water. It's too cold, as in Mars today, it freezes out.
Within our solar system, the habitable zone is relatively narrow, beginning well outside the orbit of Venus and ending short of the orbit of Mars. If the Earth were just 5% closer to the Sun, it would be subject to the same fate as Venus: a runaway greenhouse effect with temperatures rising to nearly 900 degrees Fahrenheit. Conversely, if the Earth were 20% farther from its home star, carbon dioxide clouds would form in its upper atmosphere, initiating the cycle of ice and cold that has sterilized Mars.
The presence of liquid water is a necessary condition for life, but it's not a sufficient condition. After all, there may be liquid water under the frozen surfaces of Mars and Jupiter's moon Europa, but there's very little chance that complex life exists in either of these places. You see, contrary to what the Copernican principle might suggest, the recipe for life is much more complex than just add water.
If a recipe for a planet capable of supporting complex life really did exist, then what ingredients beyond liquid water might be required? The list of necessary factors continues to grow.
We live on this paper-thin crust. If the Earth's crust were significantly thicker, then plate tectonic recycling could not take place.
The Earth's crust varies in thickness from about 4 to 30 miles. It consists of more than a dozen tectonic plates that are in constant motion. This dynamic geology regulates the planet's interior temperature, recycles carbon, mixes chemical elements essential to living organisms, and shapes the continents. Deep within the Earth's interior, the movement of liquid iron generates a protective magnetic field essential to complex life. If our planet was smaller, its magnetic field would be weaker, allowing the solar wind to strip away our atmosphere, slowly transforming the Earth into a dead, barren world much like Mars.
We need an oxygen atmosphere, and the oxygen-nitrogen atmosphere that the Earth has is necessary for complex life.
As seen from space, the Earth's atmosphere glows as a thin blue ribbon of light. Measuring less than 1% of the planet's diameter, it is composed of a mixture of nitrogen, oxygen, and carbon dioxide. As a result, our atmosphere assures a temperate climate, protection from the sun's radiation, and the correct combination of gases necessary for liquid water and complex life.
For a size of planet like Earth, our moon is big. The current thinking is that if our moon didn't exist, neither would we.
1/4 the size of the Earth, the moon's powerful gravitational pull stabilizes the angle of its axis at a nearly constant 23.5 degrees. This ensures relatively temperate seasonal changes, and the only climate in the solar system mild enough to sustain complex living organisms.
if we find life out there, especially complex or even intelligent life, it will be around a star similar to our own.
We orbit what is known as a spectral type G2 dwarf main sequence star. It is well suited for our needs. If the Sun were less massive, like 90% of the stars in the galaxy, the habitable zone would be smaller. To remain within its boundaries, the Earth would have to be positioned closer to its star. Here, increased gravity would lock our planet's rotation into synchronization with its orbit. While one side of the Earth continually faced the Sun and increased radiation from solar flares, the dark side of the planet would lay shrouded in perpetual cold and ice. It is unlikely complex life could tolerate these drastic extremes in temperature.
A lot of things went right on Earth to have yielded complex life, absolutely.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
We find that we need to be at the right location in the galaxy, that we're inside the circumstellar habitable zone of a star, that we're in a planetary system with giant planets that can shield the inner planets from too many comet impacts, that we're orbiting the right kind of star that's not too cool or not too hot, that we're on a planet that has a moon that can stabilize the tilt of its axis, that we're on a planet that's a terrestrial planet, a planet that has a crust that's just thick enough that it can maintain plate tectonic activity, that has enough heat in its interior that it's still circulating its liquid iron core so it can generate a magnetic field, that it has an atmosphere that has enough oxygen to allow for complex organisms to survive, that it has enough water and enough continents to allow for the diversity of life or an active biosphere that you need to support complex creatures such as ourselves. All these factors have to be met at one place and time in the galaxy if you're going to have a planet as habitable as the Earth, which you need for complex and even technological life.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
If every element has to be there at the same time, you have to multiply the probabilities. And that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to minus 15, which is 1/1000th of 1 trillion. And it's a number like that that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
While a growing body of scientific evidence may support this hypothesis, does the possibility that our planet is rare within the galaxy imply anything about its significance? Recently, astronomer Donald Brownlee considered this question in the best-selling book Rare Earth: Why Complex Life is Uncommon in the Universe.
There's a general feeling that nature wants to make Earth-like planets, and that naturally that life will evolve on them and naturally evolve to something like us. And yet the conditions, the environmental conditions on the planet that would allow more complex creatures similar to people or plants and animals is very rare. And so we wrote the book Rare Earth to point out that the Earth is actually a rather special place.
Brownlee contends that while relatively simple microbial life may thrive on planets throughout the universe, planets capable of sustaining complex life are exceedingly uncommon.
Well, the entire universe is highly hostile to life. If you compare all the known places in the universe, none of them compare to Earth. We live in a very special environment that provides what we need, provides air, provides food, stable conditions, so that the Earth is almost like a giant organism where its systems are interacting in a way that allows animals to survive. The real question is, why did this happen? Was it just a matter of luck or not? If you look at thousands of planets, only a small fraction of them, very small fraction, will be truly Earth-like. So if we are very rare, we did win the cosmic lottery. So we're a lucky planet. We're just in a very fortunate place.
When you consider chance as an explanation for a planet like Earth, you have to look at it in the context of the universe as a whole. While the odds appear astonishingly small that you'd get all the right ingredients to support complex life at this one place in the galaxy, you have to keep in mind that our galaxy is just one of perhaps 100 billion galaxies in the observable universe. Still, logically, I think you have to ask yourself, what if this convergence of factors didn't come about as the result of simply a cosmic lottery or a mere fluke or luck, but what if it's the result of some larger underlying purpose or design? And if the Earth does exist for a purpose, is there any way that we could tell?
On October the 24th, 1995, a rare natural phenomenon unexpectedly triggered a unique search for an answer.
Oh, look at this sky! It started with an experience I had in 1995. I went to observe a total eclipse of the sun in India. It was my first and still only total eclipse of the sun. It was a spectacular event. It's just an experience for all the emotions. Either astronomers who can understand the whole phenomenon can predict it to within a second of time anywhere on the Earth, or a local native are equally in awe and reacting in the same way to this incredible phenomenon. It really left a big impression on me.
For 51 unforgettable seconds, Guillermo Gonzalez and thousands of others looked on in wonder at this rare astronomical event. Gonzalez would later reflect upon both the mysterious beauty he had witnessed in the North Indian skies and the factors that had made it possible.
Fabulous! Fabulous! The requirements for producing a total eclipse of the sun are a luminous body, in our case the sun, an eclipsing body, in our case the moon, and then an observer platform, in our case the surface of the Earth. And they all have to be in a straight line in space. The apparent size of the moon in the sky has to be almost exactly the same as the apparent size of the sun in the sky. They're both about half a degree. The sun is 400 times bigger than the moon, but it's 400 times further away. So there's this coincidence people have noted for centuries, but they just said, oh, well, it's a coincidence, and shrug their shoulders.
As Gonzalez examined this rare alignment of sun, moon, and earth, he recognized the importance of these celestial bodies to the existence of complex life on our planet. The gravitational pull exerted by our moon, for example, is strong enough to regulate the Earth's climate by stabilizing its tilt and helping to circulate the warm and cold waters of its oceans, while our planet's distance from the sun permits both liquid water and an oxygen-rich atmosphere.
You have to have the right distance of the observer's home planet from its host star, and you have to have a large moon, and so there's this very strong overlap between the requirements for producing eclipses and the requirements for habitability, for having a planet that can support life.
In 1999, Gonzalez described this relationship between our survival and our ability to observe solar eclipses in the journal Astronomy and Geophysics. His ideas intrigued philosopher Jay Richards.
I've been focusing my research in cosmology, and in particular on applying probability theory to the fine-tuning of the laws of physics. I had a strong sense that this evidence pointed toward some sort of wider purpose to the universe. Then I read Gonzalez's work, and I had the same feeling that he did, that perfect solar eclipses were sort of the tip of the iceberg, the first instance of an entire class of evidence that provides a way for judging if the universe is the result of a fluke or some impersonal process or the result of purpose or design.
In the summer of 1999, Gonzalez and Richards initiated a program of joint research. They began their study by considering a characteristic of solar eclipses little known outside the scientific community. These striking events are not only compelling to observe, they also open a portal onto the physics and chemistry of the entire universe.
Really, you can think of eclipses as a giant natural experiment set up that allows us to observe a part of the sun that's critical towards understanding how its light is produced in its atmosphere.
The fact that the Earth is going around the sun and the moon is around the Earth, and the sizes and the distances between the Earth and the moon and the sun are just so to give you a perfect solar eclipse is a wondrous thing, because it allows us to measure the constituents of the upper layers of the sun's atmosphere.
During a solar eclipse, the moon fits so perfectly over the sun that it shields its blinding light, providing astronomers with a view of the star's atmosphere otherwise impossible to experience. At the moment of totality, the pinkish arc of the chromosphere, the atmosphere's innermost layer, becomes visible, and with it a rainbow-like band called the flash spectrum appears when the sun is viewed through a prism. The eclipse of 1870 led to an understanding of the structure of the sun's chromosphere and the discovery of helium, the second most abundant element in the universe.
The spectrum is probably the single greatest source of information about a star. And it was during a couple of historic eclipses in the 19th century that astronomers figure out how the spectrum of the sun is produced. And they only were able to figure it out because of the particular circumstances during a total eclipse.
These circumstances are both precise and crucial. If our moon was slightly larger, it would partially block our view of the chromosphere and diminish its spectral light. A smaller moon would allow too much light from the sun, destroying our view of the solar atmosphere and the flash spectrum.
And so you have to have a nearly perfect match between the sun and the moon, so you don't hide the chromosphere. And that insight afforded by eclipses in the 19th century is what finally permitted astronomers to figure out how the spectra of distant stars are produced. Really, that opened up stellar astrophysics and allowed us to understand how other stars work, because distant stars, after all, are other suns.
The relationship between eclipses and scientific discovery was also revealed in the spring of 1919. On May the 29th, research teams headed by British astronomer Arthur Eddington photographed the sun and adjacent stars in the Hyades star cluster during darkness of totality. Later analysis of the pictures verified that the sun's gravity bent light from distant stars traveling toward the Earth at the angle Albert Einstein had predicted. Einstein's theory of relativity, an idea that revolutionized our understanding of the universe, had been confirmed during a total solar eclipse.
And that experiment was only possible because the stars become visible during a total eclipse. They're very important in the history of science. And the best place in the entire solar system to view solar eclipses is from the surface of the Earth. I've actually calculated the circumstances for eclipses from all the other planets and all the other moons, about 65 of them, the major moons. And it's an amazing coincidence. The one place that has observers is the one place that has the best eclipses.
Within the gossamer light of a solar eclipse, Gonzalez and Richards recognized a fascinating connection between the factors necessary for complex life and scientific observation. But was this merely an isolated fluke of nature, or a glimpse at a principle and a purpose fundamental to the universe as a whole?
That was the million-dollar question that we continually had before us. What if those things that make a planet habitable also make that planet the best place for making scientific discoveries? That is, what if those rare locations in the universe that are compatible with observers like ourselves are also the best places overall for making observations?
For 3 years, Richards and Gonzalez meticulously tested their idea against evidence gathered from a wide range of scientific disciplines. In the 2004 book, The Privileged Planet, they published their hypothesis. The same narrow circumstances that allow us to exist also provide us with the best overall setting for making scientific discoveries.
In the book, we detail more than a dozen examples of this correlation between life and discovery. And these aren't quirky, marginal examples. Each treats a condition critical to its respective scientific field. Some deal with remote things, like the nature of galaxies. Others are much closer to home.
While a perfect solar eclipse was the catalyst for Gonzalez and Richards' hypothesis, their observations would never have been possible without another, more familiar example of the correlation between life and discovery: the atmosphere of the Earth.
It's striking when you see pictures of the Earth from the Apollo missions or other spacecraft, and you see this very thin layer of the atmosphere surrounding the Earth that sustains all the life that we know on Earth. And so you need a certain mix of elements to support a complex biosphere like ours. Not just any atmosphere will do.
Our appreciation of the Earth's atmosphere has increased significantly during the last 40 years as exploratory spacecraft have probed the solar system. These missions have confirmed that within the Sun's family of more than 70 planets and moons, the Earth is one of 7 bodies enveloped by a thick canopy of gas. Yet among these 7, only the Earth's atmosphere can sustain complex life. And only the Earth's atmosphere is transparent.
It's an atmosphere that's made up of mostly oxygen and nitrogen with very little carbon dioxide and very little other carbon compounds or atoms in the atmosphere that gives you a transparent atmosphere. If we had too much carbon in the atmosphere, we get hazes, organic hazes in the atmosphere, like you see on the large moon Titan, for example.
The dense shroud of gas that blankets Saturn's largest moon resembles the atmospheres surrounding Neptune, Uranus, Saturn, Jupiter, and the greenhouse cauldron of Venus. None of these alien worlds know the stars, or even offers a clear view of the sun.
Now, of course, if you were suddenly transported to Titan or Venus or to one of the outlying gas giant planets, the lack of a clear view of the universe wouldn't be much of an issue because you'd be dead. But that's precisely the point. If we're right, if the conditions for habitability and scientific discovery appear in the same places, then you're going to get conditions like you do on Earth, an atmosphere that sustains complex life like ourselves and also enables scientific discovery of the universe around us.
The virtues of such an atmosphere are continually tested. As the Earth moves through space, it is bombarded by radiation from throughout the universe. This radiation is emitted by the Sun and other celestial objects, including supernovas and distant galaxies. It reaches our planet in wavelengths described as gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio. Together, they comprise the electromagnetic spectrum. Almost all of these wavelengths are invisible to the eye and either lethal or useless to organic life. Yet within this spectrum of frequencies, a thin sliver of radiation proves essential to plants, animals, and human beings.
In other words, there's really just a very narrow part of the electromagnetic spectrum that's going to be useful for living processes like photosynthesis. It's not as if life could have evolved to use gamma radiation or X-ray radiation or something like that. There's really just a narrow part of the spectrum that would be useful to life processes. Well, as it turns out, that's also the same narrow part of the spectrum that is the most informative about the various structures that we discover in the universe around us.
These specific frequencies that enable plants to manufacture food and astronomers to observe the cosmos represent less than 1/trillionth of a trillionth of the universe's range of natural electromagnetic emissions. Fortunately, it is the type of light our sun produces in abundance, and that most easily penetrates the filtering shield of our atmosphere to reach the surface of the Earth.
It's a remarkable coincidence that the kind of atmosphere that's needed for complex life like ourselves does not preclude that life from observing the distant universe. It's a surprise. It's something that you wouldn't expect just chance to produce. Why would the universe be such that those places that are most habitable also offer the best opportunity for scientific discovery?
In 1997, Guillermo Gonzalez began a study of the Earth's specific location within the Milky Way galaxy. It would eventually lead him to more evidence of a correlation between life and discovery.
Just as our location in the solar system is optimized for habitability, so is our location in the galaxy. We inhabit a spiral galaxy, which means it's highly flattened. It has a spherical bulge in the center, and it has spiral arms. And we live about halfway between the center of the galaxy and the edge.
Working closely with astrobiologists Peter Ward and Donald Brownlee, Gonzalez compared our position in the Milky Way to other regions within an often hostile galaxy.
The galaxy has a lot of dangers, and perhaps the most dangerous place in the galaxy is the galactic center.
Well, in the center of the galaxy, this density of stars is very high, and there are more supernovas and stuff. And there are things that could harass life right in the dead center regions of our galaxy.
You also have the giant black hole at the very center of the galaxy. And if it were to have a close encounter with a star passing near it, it would rip to shreds and form an accretion disk around it and emit lots of radiation, particle radiation and electromagnetic radiation, gamma rays, X-rays.
While a black hole, exploding stars and deadly radiation would make complex life virtually impossible near the galactic core, the outer edge of the Milky Way poses other challenges to habitability.
In the outer regions, the situation is much more subtle. We live on a planet made out of iron, magnesium, and silicon, and oxygen. If we went in the more distant regions of our galaxy, out towards the outer edge, the abundances of these elements are lower.
There probably aren't enough heavy elements to build Earth-sized planets that can support life. So there's a happy median between the dangerous galactic center and the outer edge of the galaxy.
Gonzalez, Brownlee, and Ward labeled this region, where complex life is possible within the Milky Way, the galactic habitable zone. Their theory was first published in 2001 and has since received growing acceptance among astrobiologists.
There's a lot more research that needs to be done to determine just how wide the habitable zone is. But I think there's general agreement that yes, there are definitely places in the galaxy that you cannot have civilizations because they're very dangerous. And there are places where you just have a very low abundance of heavy elements.
While these obstacles to habitability are minimized far from the core and edge of the Milky Way, Gonzalez has also identified large areas within the galactic habitable zone itself, which are less hospitable to complex life.
Even within the habitable zone in the galaxy, it's broken by the spiral arms, which are dangerous places. That's where most of the supernovae go off in the galaxy. That's where the star formation is taking place.
We don't want to be too close to a spiral arm. We want to be outside the spiral arm at about the right region of the galaxy.
It appears this is precisely where the Earth is located, in the relatively safe and uncrowded region between the Sagittarius and Perseus arms of the Milky Way.
Location is everything, and so we occupy that special place in the galaxy where habitability is optimized, threats are minimized, and we have enough building blocks to build an Earth.
Guillermo Gonzalez and Jay Richards have conducted research on another facet of the galactic habitable zone. They now argue that the Earth is also located in the best setting within our galaxy for astronomical research.
As it turns out, our position in the universe is not only critical for life, but it's also surprisingly important for making scientific discoveries. We're located near the midplane of the galaxy, a very highly flattened galaxy, between spiral arms in a region with very low dust extinction. While we are in the plane of the galaxy, that does not obscure a large part of the sky, so we can have very clear views.
For more than a century, this nearly ideal platform of observation has enabled astronomers to study the structure of the Milky Way. Looking toward the constellation Sagittarius on a clear night, for example, we see that the stars in our galaxy are not uniformly distributed across the sky. Instead, they appear as part of a concentrated band, a flattened disk of stars, dust and gas, 100,000 light-years in diameter.
The Milky Way band in the night sky is us looking edge-on into the plane of the galaxy. If we were living in the center of the galaxy, things would look much more spherically distributed. And so it will be very hard to distinguish things that are inside the galaxy from things that are outside. And it's also very dusty, much dustier towards the galactic center than it is in our region. And so the views of the distant universe will be much more difficult to obtain, to be much more compromised.
Similar problems would exist for astronomers working on a planet located within any of the galaxy's spiral arms. Here, denser concentrations of dust clouds and gas illuminated by stars would make it difficult to determine the shape of the Milky Way, or to distinguish the stars in our galaxy from the rest of the universe.
On the surface of the Earth, we're really in the optimum position for seeing both the nearby structure of the Milky Way galaxy, as well as seeing the distant cosmos as a whole. So once again, we see that the best location for habitability and for producing a habitable planet is also the best overall position for scientific discovery, in this case, at the galactic scale. For centuries, the fact that we can discover things about the universe has really been something of a mystery. Why would beings like ourselves be able to discover a universe like this? Why is what we think about the universe, why would it correspond to the way things really are?
Our ability to discern and understand the universe is a fundamental part of what makes the universe tick, so that we're linked into it. This isn't just a sort of an accident, a trivial little byproduct. It is something that is linked to the great cosmic scheme of things. Now, I've no idea how that linkage works, why it's there, or anything of that sort, but I'm very, very struck by the fact that we can understand the universe in such exquisite detail and at such a deep level.
The spectacular progress of modern astronomy and physics is the product of a universe accessible to the human eye and mind. It is a universe governed by laws and forces that literally hold our planet Earth and the entire cosmos together, and are finely calibrated to allow for both complex life and scientific discovery.
If you didn't have something like gravity that pulled matter together, you would never get planets, you wouldn't get stars, you wouldn't get any complex organisms. If you didn't have the strong nuclear force, there would be nothing to hold protons and neutrons together in the nucleus. And so you wouldn't have any atoms, so no chemistry. If you didn't have the electromagnetic force, you would have no bonding between chemicals. You would have no light, and the list goes on. So you need all these sorts of fundamental principles have to be in place in order for life to occur. Wipe out one of those principles, wipe out one of those laws, no life.
During the past 40 years, scientists have determined the relative strengths of each of these primary laws and forces. These strengths are so critically balanced, they are often described as being finely tuned.
If you're to take the basic fundamental constants of nature and you were to change these even slightly, or you were to pick their values at random, you would almost never get a universe that would be habitable in any sort of way. That is, you couldn't have galaxies, you couldn't have planets, you couldn't have complex biological organisms if these fundamental constants were even slightly different, slightly stronger, slightly weaker than they actually are in this universe. That's the idea of fine-tuning.
To better appreciate this concept, imagine a machine able to control the strengths of each of the physical constants. If you changed, even slightly from its current setting, the strength of any one of these fundamental forces, such as gravity, the impact on complex life would be catastrophic.
If you increased it by a little bit, no large-scale life forms could exist. Anything that was more than the size of a pea would be completely crushed. So you might be able to get life of a very, very primitive sort, such as bacteria, but you could never get conscious observers.
Now, this is one of a long list of properties in underlying physics that seem to be prerequisites for a universe with life. For example, the strengths of the other forces are all important, the masses of the various subatomic particles. If all of these things were even a little bit different, then life, certainly life as we know it, could not exist.
These forces and constants are another example of the correlation between life and discovery. For not only are they finely tuned for our existence, they can also be understood.
It's remarkable how well the laws work. And not only that, it's remarkable how simple they are. And that also is related to the discoverability of the laws.
Albert Einstein wrote, "I have deep faith that the principles of the universe will be both beautiful and simple." For nearly 400 years, scientists have discovered an elegant simplicity in the mathematical equations that express and unlock the laws of the cosmos.
It's been said that many of the most important theories in theoretical physics can be written on a single sheet of paper. And this, I think, ought to be considered surprising, that such a simple formula or equation could have such far-reaching applications to a very complicated and very large universe.
What you have is a universe that is not only finely tuned for life to occur, but also has a beautiful, elegant mathematical structure, and a structure such that we can discover that structure.
Most scientists just take it for granted that the world is both ordered and intelligible. And the intelligible part I find really quite extraordinary, because it's one thing to accept that the universe is ordered, but ordered in a way that human beings are capable of understanding is an extraordinary thing. And so the question naturally arises, what is the explanation for that?
Many who have pondered this mystery of an intelligible universe argue that it cannot be easily explained away.
From naturalistic assumptions, you would not expect the universe to be understandable by human reason. After all, within the standard naturalistic story, human reason was developed to be able to hunt prey, get around in the everyday world, attract mates.
We have certain skills, for example, we can jump streams and catch falling apples and so on, which are necessary.
Perfect positioning, so we can comprehend it all. But from my old skeptics days, it would have had to have been just dumb luck. That's why I quit being a skeptic. But this information that has come out in the last 30, 40 years is even more than the classical kind of explanations for God's existence that you see in your notes. Those are your classical arguments that you have been reading, I hope. And by next week, you'll be to page 25, and we will be jumping into that about 2 weeks from now. Now, next week, we go into the fossil record. We go from telescopic to microscopic. We go to the fossil record, to the DNA, the intelligence that is built into the DNA, the information systems in the DNA. And so we start on kind of a new groundwork, a new way of looking at the probabilities that are involved in saying that there is the high likelihood that some intelligence is behind this. Where are we trying to take our preponderance of evidence then is taking the non-believer or skeptical mind, like I used to have, into a position where he or she is if he's going to be objective, and the last thing you want to do is be prejudiced. That's a bad thing in a courtroom. And remember, we're trying to think of this as evidentiary. To be fair, what you want to do is have an open mind. That's all that we're asking for, and to let the evidence speak and take you where it will lead you. So next week you have that. Please remember to do your homework, especially this James White thing. Take a look at that, and we'll see you next week. Thank you.